All right, so this is going to be a lesson about implicit differentiation. In OpenStax, this is section 3.8. Let's start with an equation. Let's look at xy equals 1. The graph of this equation is shown over here. If you pick a point on this graph, let's say you pick this point right here, that's going to be some coordinates x and y, and they're going to satisfy this equation. So that basically multiplying them together equals 1. An example would be like x could equal 2, y could equal 1/2, multiplied together they equal 1, or x could equal like 3/5, and x and y could equal 5/3, for example. Anyway, we have this point. And let's say that what you want to do is figure out the slope of a tangent line. So let's see, tangent line here, something like that, right? And we want to know, what is the slope? The slope of that tangent line is still going to equal the derivative of y with respect to x. That's what we've learned, evaluated at that specific point. So how do we figure out dy over dx based on an equation like this? Because all of the derivatives we've done so far have been based on like having a function. So one approach to this would be solve for y. So if we do that, we would get y equals 1 over x, or alternatively rewritten x to the power -1. Okay, so doing this, solving for y, makes it so that we can essentially express this as a function. We could have written f of x equals x to the -1, and then we can apply all of the familiar differentiation rules. We could say dy over dx equals -1 times x to the power -2, or -1 over x squared, right? So okay, so we can find our derivative that way. But this here, this is not what the section is about. This here is explicit differentiation. It requires that you have an explicit format for the function. So right here, when we have y written down as a function of x, that is the explicit form. But what we were originally given here, this was an implicit form. It's not explicitly telling us how to calculate y as a function of x. It's an implicit form. It's an equation of x and y, and it's implied that if you give it x as an input, it will produce a y as an output. An implicit form is a little bit more powerful than an explicit form, because with an implicit form, it's possible to have like multiple y outputs to the same x input. An example would be like the equation of a circle. We'll do that in a later video, perhaps. But for now, what I want to show you is that there's an alternative approach to taking derivatives that doesn't require that you first solve for x, solve for y. All right, so the alternative approach is this implicit differentiation idea. Here's how it works. Start with your equation. X times y equals 1. The first thing we want to do is we want to take the derivative of both sides of this equation. If the two expressions are equal, their derivatives will also be equal. Just like how you can add something to both sides of an equation, multiply by something on both sides of an equation. Same idea. So if I take the derivative of both sides of this equation, I can write that using some sort of operator notation. So for example, we could write d over dx, using the Leibniz operator notation. We could say, and that means, now we have the derivative of the left side, and that will equal the derivative of the right side. So now we need to actually take the derivative, right? And that's a little bit, that can be a little bit deep. One thing we need to keep in mind is that there's an implied relationship between the variables. When we're trying to take a derivative of y with respect to x, right? We're trying to get this dy over dx. We want to think of y as a function of x. Y depends on x, except that's not explicit in this equation, right? So we want to think of this idea as like implied. So implied, all the time we should be thinking y equals some function of x. Okay, we don't have a formula for that function explicitly, or at least, obviously in this example we could have gotten one, but we haven't. Okay, let's pretend we don't know that yet. We're not going to get that. So that means y depends on x. So here, right here, it's x times y. Both of those are functions of x. X is dependent on x. It is y, which is dependent on x. So that is going to be a situation where we need to apply product on the left side. So we're going to say the derivative with respect to x of x, that's the first function, and then we'll multiply by y, and then we'll add x times the derivative with respect to x of y. So that's applying f prime g plus f g prime, familiar product rule. I'll write that underneath it so you can see the format there. So that's our product rule. Now on the right-hand side of the equation, we have the derivative of 1. That's just 0. There we go. That's just 0. So now we can say, well, let's do these derivatives of these little individual pieces that we have left. We still have to do the derivative of this here, and we still have to do the derivative of this here. So on the left, we have derivative with respect to x of x. That's a nice easy one. That's just equal to 1. Right? We have 1 times y plus x times, now what do we do here? This is the weird part, because here we want to do the derivative of something, but the thing we want to do the derivative of is y. Y is implicitly a function of x, but we don't have that explicit formula. And we're not going to go back and do it like this, like we did last time. Instead, we're going to say, well, isn't our goal to find dy over dx? That's the goal. And that's what this is right here. It's just the derivative of y with respect to x. So since that's our goal, let's just write it in there by its name without actually doing anything, without doing a derivative as you think of it usually, right? Let's instead just write it in here as a placeholder and say whatever is going to go there, that's the derivative of y with respect to x. Because now that we've done that, now the result here is an equation that involves x, y, and also this new thing, which is derivative of y with respect to x. We can solve it for that dy over dx. So we're going to take that, and now we're going to solve that for the dy over dx. All right. So the first thing I would do is like subtract y from both sides. I have x times our dy over dx. And then I'm going to subtract y from both sides. This is equal to y here. So I'm going to have equals negative y, right? Then I'll divide both sides by x. I should write down here, I'm subtracting y. I'm subtracting y. And then we're dividing both sides by x. And so what we end up with is dy over dx equals negative y over x. All right, so we got an answer. So here we go. I'm going to put a box around that answer. That is our derivative of y with respect to x. But also we had this one. Oops. This one here. All right. Earlier we did it in the explicit way, and we got negative 1 over x squared. That seems pretty different from negative y over x, doesn't it? At first, perhaps it does. But remember, we've already found with using like the product rule versus using the quotient rule. Sometimes you're going to use the quotient rule. Sometimes you can simplify something and just use the power rule. There's often like lots of different ways, or at least a few different ways to do a derivative, and the resulting expression might look different, and yet they will be equivalent to one another. However, this time there's a more significant difference. In fact, that this is an expression in terms of x and y, right? Whereas this up here, this is x only, right? So if we wanted to get this derivative of y with respect to x in terms of x only, we would have to resort back to doing some sort of an explicit formula. Okay, so the power of implicit differentiation is that it lets you differentiate without having to solve for y first, which can be really useful. The downside is that the result is involved a function of x and y, which is maybe not ideal, but that's okay. In this case, we can actually replace the y with 1 over x, and you will see that a little bit of algebra simplifies this to negative 1 over x squared, and it is in fact the same as the previous answer. All right. So in the first half of the video, I explained this idea of implicit differentiation with an example, and I showed you the difference between implicit form and explicit form, right? And demonstrated that when we solve for y and take a derivative explicitly, we get the same answer as we did when we solved for the derivative implicitly. But solving for y is not always possible. So an example of that is a 5th degree polynomial. You know how we have the quadratic formula, which basically shows you how you can solve for the solutions of any quadratic equation, right? You can find the zeros of any quadratic function. There's also a cubic formula and a quartic formula for degrees 3 and degree 4. But for degree 5 or higher, there's a theorem called the Abel-Ruffini theorem, or otherwise known as Abel's impossibility theorem. And it says that it's impossible to come up with a formula that'll give you the solution for any 5th degree polynomial. Here's an example of a 5th degree polynomial in the variable y. It's impossible to solve this equation for y, at least not using algebra, right? So this is an example where this is still a valid thing, like this is still a perfectly valid function or equation, and we can even look at the graph of it. Here, I'll get the graph up, show you. It's an interesting looking graph, actually. It has 2 parts: y to the power 5 minus y minus x squared equals 0. It has 2 parts to it. It has a part down here. It has a part up here. But these 2 parts are both smooth. They're continuous, individually, and so you can find tangent lines to them, right? So the idea of a derivative should still work. It's just that we need to apply implicit differentiation strategy. So I'm going to rewrite both sides of the equation, but I'm going to say let's do the derivative of x of the left side and the derivative with respect to x of the right side, like that. That's always the beginning of our implicit differentiation work. So now we can apply some of the basic differentiation rules that we know. The first one I want to use is the sum and difference rules that say you can split up a derivative over the sum and difference functions. So I'm going to have derivative of y to the power 5, and I'm going to minus the derivative of y. This is with respect to x, remember. The derivative is with respect to x, despite the fact that these are functions of y. Okay, that is notable. Then I'm going to have minus the derivative of x squared, and then equals the derivative of 0. Now the derivative of 0, I'm going to go ahead and key that one. That should be 0, because 0 is a constant, and so its derivative is still 0. Okay, so now I've got to deal with this left-hand side over here. I have these 2 places where I'm talking about the derivatives of y, different functions of y. And then here I'm dealing with the derivative of a function of x. So I think it's going to be easiest to start with our rightmost So the derivative of x squared with respect to x is just exactly what we're used to. Just doing the power rule, it's just 2x. And we're subtracting that. Okay, so that's that. Now, the next term going from right to left here, this one, the derivative with respect to x of y. Like I said in the previous example, that's the goal, right? The goal is to find dy over dx. So that thing, the derivative of y with respect to x, that is just that. We could just write it like that, okay? And we're going to end up solving for that in the end. Okay? And now let's do this one. So here we have not just the derivative of y with respect to x, but rather the derivative of y to the power 5 with respect to x. This is actually a composite function. This is composite. Maybe not look like it, but it's composite. The outer function, it's like f of g of x, where the outer function f of u equals u to the power 5, and the inner function g of x is equal to y. Now that's quite it's a different arrangement than we've seen before, but it's still a composite function. Because remember, imply is this in this scenario is this idea that y is a function of x. Okay, so we've got to treat it that way whenever we encounter it. So the way I'm going to do the derivative of that, I'm first going to apply the power rule to do the derivative of y to the 5. So that's pretty normal. I'm just going to do 5 times y to the power 4, right? But then via the chain rule, because this is a composite function, via the chain rule, we have to multiply by the derivative of y with respect to x. Yet again, that is dy over dx. Like so all right, so whenever we encounter a function that involves y, we have to use the chain rule, where we are applying, like we're doing the derivative of that function, but then we are multiplying by the derivative of y with respect. Okay. So now what we have is an equation, and it has all these parts that involve x and y, and then it also has a few places where you've multiplied by dy over dx. The result here will always be a linear equation with respect to the dy over dx variable. So we should always be able to easily solve for dy over dx. And the strategy for doing that is going to be just to gather all of the terms that involve dy over dx on one side of the equation. So in this example, they're both already on the left side. Great. And then take any term that doesn't have a dy over dx, gather those on the other side of the equation. What I'm going to do is I'm going to add 2x to both sides, so that I cancel out 2x from the left side of the equation and put it over to just the right side. I've got 2x over here. And on the left, I have my 5y to the power 4 times dy over dx, and then minus another dy over dx. Nice. All right, so on the left side of the equation, now all of our terms had exactly one factor of dy over dx. So what can we do? Well, we can factor it out, of course. So we're going to introduce some parentheses here. We're going to factor out the dy over dx and put it on the outside of the parentheses. What we have now is dy over dx out here multiplied by the expression in parentheses 5y to the power 4 minus, well, I guess minus 1, right? And then that all equals 2x. And so now the very last thing you can do, and I say, I'm saying this about this example, but also about all examples. Okay, every time you're doing implicit differentiation, the last few steps are going to feel very similar. Always going to be gather up all the dy over dx terms, factor out dy over dx, and then whatever you have left here after factoring out, divide both sides of the equation by that. So we're going to divide by 5y to the power 4, 5y to the power 4 minus 1, so that it cancels here. And we obtain our final answer. Dy over dx equals 2x divided by 5y to the power 4 minus 1. And that is our derivative of y with respect to x. formula. I'll bring back the graph here. It's a formula that that tells us the slope of a tangent line for any point on this graph. Let's pick a point on the graph. Let's see if we can pick one. Here's a point, 0.731, negative 0.669. All right, I'm going to demonstrate to you how we can use this answer that we got. Okay, so let's see if I can. Should be able to do something very clever like that. There we go. And I'm going to move my face up there. And over here, okay, so I'm going to grab one of these interesting points. Let's find a good one here. I'm going to get that, 0.518 and negative 0.917. Okay, there's a point which is approximately on the graph. Now what I want to do is I want to use that as my x and that is my y. Okay, so I'm going to make a formula, a fraction. I'm going to 2a divided by 5b to the power of 4 and then minus 1. So I'm using a and b in place of the x and the y. And then I'm going to have a equal to x value, so that's 0.518. And b is going to equal the y value, that'll be negative 0.917. Negative 0.917. Okay, and this formula that I made, I'm going to call that m. Okay, so now m equals that. So what I should be able to do now is I should be able to go ahead and write an equation for a tangent line. Y minus the y coordinate, actually going to be plus 0.917, okay, equals this new slope formula that I just did, m, and then times x minus the x coordinate, 0.518. And let me just make that a different color, make it red dotted. And there we go. I'll make this full screen. And you can finally see that that point right there, it's on the graph of the function. And this line we've made has the right slope because we used the formula that we found by implicit differentiation. So that's pretty cool. I'll zoom this out so you can see everything I did here. And you can try that sort of construction on your own as well.